All right, it's my great pleasure to moderate today's setup panel on satellite interference. And I would like to welcome our panelists here. First, we have online Genoveva Micheva, the foremost instrument scientist at the Leibniz Institute for Astrophysics. Then we have, hopefully joining us in a few minutes, Zuhair Ben Khaldoun, the director of the Orchomeden Observatory at Qadi Ayad University in Marrakesh. We have David Vincent Stark, who is working at the Space Telescope Science Institute, and he's going to talk about HST, so Hubble Space Telescope interference. We have Samuel Spencer here, who is research assistant at the Friedrich-Alexander-Universität in Erlangen-Nuremberg, who is going to present us with a very interesting view on gamma-ray astronomy. And last but not least, Benjamin Winkel from the Max Planck Institute for Radio Astronomy in Bonn, Germany. Please have a seat, my dear panelists. Welcome our panelists online. I hope you can hear us. All right, so the way this is working is the panelists will get about 5 minutes each to give brief introductions of themselves and over their research field. Then I get dibs on the first round of questions, and then we'll open it up to the audience so you can have a nice discussion with our colleagues here. So, Genoveva, would you like to start?
Yes, I hope you can hear me.
Perfect.
Okay. So my name is Genoveva. I'm the instrument scientist for Foremost. And if you don't know Foremost is a spectroscopic survey instrument that's we're currently preparing to go into commissioning next year. And the problem that I want to talk about is the problem that Foremost has with the satellite constellations, which can be summarized as follows. So Foremost is a spectroscopic instrument, and it has a very large field of view. It's about 4.2 square degrees. That means that for every exposure, we're actually seeing a pretty large chunk of sky. But unlike the LSST, our exposure times are very long in comparison. They're 20 minutes, right? And this is necessary because we are fiber-fed spectrograph, which means that we have these tiny fibers that need a long time to get light in them, right? There's just a tiny fraction of light that goes in them. And we also have 15 arc seconds between the fibers, right? So between the minimum distance between two fibers is 15 arc seconds. But we have 2,436 fibers. So spread over that field of view, together with the long exposure time, all of those things combined means that on average, if a satellite passes the field of view of Foremost, it will hit 1.3 fibers. Now you may think, well, 1.3, that's a very small number, and it is, but Foremost is going to be the only instrument on the Vista telescope, which means that we will be observing every night, all night for like the next 15 years. And that's going to be a lot of data, but it will be spectral data. So there is no spatial information. And that means that it's going to be difficult to see any satellite trails. And therefore, it's going to be difficult to know which fibers were hit. And we need to know which fibers and therefore which spectra are contaminated with satellite contribution so that we can throw those spectra away. So from our science case perspective, we're going to throw those spectra away. But from the perspective of somebody who wants spectra of satellites to have another form of observation of satellites, of course, that's probably not garbage. But we have to flag those contaminated spectra, because if we don't, then you can never ever take an individual spectrum from Foremost and studying it on its own, right? Because you never know, is this contaminated? Am I really looking at a star in the LMC that has these weird features, or is it simply a normal star that has a satellite contamination on it? So in order to know if we can do that, or to prepare how we're going to do that, we first investigated if we can automatically detect satellite contamination, because if we can, then we still lose data, but at least we know which data we lose, and then we're good to go. And what we did is we simulated Foremost spectra. We took real targets from Foremost surveys, and then we made one night of data with where every single spectrum in every single observation had some random contribution by a satellite of different brightness. And then we took that same night, but without any contamination whatsoever. And then we, of course, reduced both nights and derived all the stellar properties from both nights. And then we compared those stellar properties. And the stellar properties that we concentrated on were stellar radial velocity, the chemical abundance, the effective temperature, and the gravity. And unfortunately, we found that specifically for the stellar radial velocity and the chemical abundance, we saw a difference. So when we compare the radial velocity of stars that are from the reference spectrum that is uncontaminated to the radial velocity of stars in the contaminated spectra, to those same stars, of course, we find a difference. And that difference, unfortunately, is kind of impossible to detect automatically, because the difference is on the order of 5 kilometers per second, 10, 15, up to 30 kilometers per second. It can be plus minus that. And there are many stars in the universe that we're going to observe that have that kind of radial velocity. So it's not like a machine or even a human being seeing that radial velocity can say, well, okay, this is a contamination. So what this means is that we clearly need an imager, and we are in the process of adding an imager. We're going to add a little camera with its own telescope to Foremost. And then we've already done the preliminary study of the requirement specifications for the camera together with the telescope. And we're now starting to think on how we'll detect those satellite trails, because we need to detect them in real time. And then, unfortunately, we're going to throw the data away, right? So unfortunately, our plan is take images, analyze them, throw them away, and then with the analysis, just detect which fibers are hit from satellite trails, and then flag those spectra in our database. And the reason we're going to throw data away is because we are in no position to absorb that kind of data flow and data storage and just data maintenance that was completely not planned for when Foremost was designed. And we just do not have the capacity to actually take care of that data, even though it will probably be interesting, because it, like I said, we'll be observing all the time, taking exposures every 3 seconds, I think it was. But yes, that's why we need an imager. Thank you very much for your attention.
Thank you very much, Genoveva, for the introduction. Next on my list is Dave Stark.
Yeah, hi. Can you hear me okay? All right. Yeah, hi, everybody. I'm Dave Stark at the Space Telescope Science Institute. Sorry I couldn't be there in person, but happy to attend remotely. So my work in the field of satellites is assessing the rate at which we see satellite trails in HST. As we heard yesterday, despite it being in orbit, it's still below or at a comparable orbit to a lot of satellites that are up there. So we do see them in our imaging data every so often. So my efforts have been to develop a new software package to automatically identify these trails and mask them from the data. And our approach, to give you a very sort of high-level overview of how it works, it uses a modified version of what's called the radon transform. So we use something called the median radon transform. In simple terms, what we do is for every image, we look at every possible linear path crisscrossing the images, and we measure the median value of the data along that path. So most of the time, you're just going through empty sky. The median value is going to be the sky level. But occasionally, one of your paths that you're measuring the median over intersects with and aligns perfectly with a satellite trail. And so because you're combining all those pixels together, you can measure the median value of the satellite trail pretty down deep into the noise. So, right, what it does basically takes these long, stretched out signals and compresses them into point sources that are easier to detect. The main advantage, as I just mentioned, is that it's quite a bit more sensitive than previous software that's been at use at Space Telescope. So for the previous software, basically applied an edge detection filter to look for kind of discontinuities in the sky surface brightness, and then applied a Hopf transform to detect these linear discontinuities. So what we have is quite a bit more sensitive. At its best, it can detect a satellite trail whose average brightness is only 10% of the sky noise level. So that's getting really deep down into the weeds. And because the calculation uses a median, it's quite robust against astronomical sources, so like stars and galaxies giving false detections. Not perfect, but pretty robust. I'll mention that this is all public. The software has been released in the ACS tools package. It's all online. If you need the link, just Slack me. I'm happy to send it to you. I'd love people to download it, play with it, break it, improve it, do whatever we need to make it work really well. But yeah, the punchline here is we took this new software and applied it to 30,000 or so HST images taken with the advanced camera for surveys, the wide field channel. So this is the widest field imager on HST. And we looked at data from 2002 to 2022. And the goal here was to understand how has the presence of satellite trails changed over time? Have they been more frequent, which we expected they would be, but to what level? And is the typical brightness changing? And what we found is that between, over the last 20 years of data, the rate of satellite trails has roughly doubled in our data. So in 2002, we detect a satellite trail in about 5% of images. So this equates to a trail intersecting our data, say, every 3 to 4 hours. In 2022, we estimated that roughly 10% of individual exposures had satellite trails in them. So this is more like a trail every 1 to 2 hours. In terms of their brightness, there's not much interesting to say from our perspective. The brightnesses seem to be about the same over 20 years. So they're not really getting systematically more bright or dimmer. So yeah, I'm happy to be here and answer any questions about the work. And I'll pass it back over to you.
So the next speaker to introduce is Samuel. Please go ahead.
Yes, can you hear me? Yes, now you can, I think. So hello, everyone. I'm Sam Spencer. I'm a postdoc in FAU in Erlangen in Germany. I'm here because I was recently a co-author on a study concerning the impact of satellite trails upon HESS data. HESS is an imaging atmospheric Cherenkov telescope array, or IACT array, located in Namibia. And IACT arrays like HESS are designed to observe very high energy astrophysical gamma rays, so gamma rays with energies between about 50 GeV and 100 TeV. The way that HESS works, and other IACTs like it, is that when one of these gamma rays hits the top of Earth's atmosphere, it undergoes pair production and creates a particle cascade. These particles are very high energy. They travel faster than the speed of phase velocity of light in air, so they emit Cherenkov radiation. And then from the ground, we have arrays of telescopes with fast cameras that are designed to image this Cherenkov light as it hits the ground. So unlike, for example, radio or optical astronomy, where you're observing the astrophysical photons themselves, we reconstruct the properties of the photons that hit the top of the Earth's atmosphere by essentially measuring the properties of the air showers that we observe. And so it was important. So I should say that historically, IACTs basically never considered the effect of satellite trails. The reason for this is that IACTs are more like particle physics detectors. They operate on very short timescales. So the integration time for an IACT is typically around 10 nanoseconds. However, there wasn't any real data to suggest what a satellite trail would do to an IACT, given the sensitivity of its the light sensors in it. So we performed a study with HESS so that we could quantify the effects on our telescopes, such that when the next generation of Cherenkov telescopes, which is going to be called CTA, comes online in the next decade or so, we can predict what's going to happen. And you'll see the first of the CTA telescopes if you go on the observatory tour tomorrow. It's big, you'll see it. So what we did was we developed a new technique to basically extract satellite trails and identify satellite trails in monitoring data that we take concurrently with our short timescale observations. So our cameras have these two channels. They've got a channel that can observe light on nanosecond timescales, and then they've got basically still image frames that get taken every 0.1 seconds. And these still image frames of the sky brightness were combined with cuts and a trail finder to basically identify the time intervals when there were satellites on our camera. And then we took those time intervals and looked at the air shower events that we detected during those time intervals in our nanosecond timescale data. Basically, the sort of takeaway message is that the effect of satellite trails on IACT observations is measurable, but thankfully for the time being, with HESS at least, it shouldn't massively affect HESS operations because the fraction of observing time, given our pointed instruments and narrow field of view, which for HESS is 3 degrees, we determined that essentially our observations weren't going to be sufficiently affected to stop us doing any science. Though we can measure, for example, false trigger events where these satellite trails can get mistaken for air showers in the camera, and so these events will need to be removed. Looking forward to CTA, the trends we observe do mildly increase. We also see a roughly doubling of our number of trails in the 3 years of data we considered from 2019 to now. So CTA could still be affected given the increasing number of trails. However, this is dependent upon the analysis techniques that you use, and with HESS we can only do so much and say so much. So more work is still needed in gamma ray astronomy.
Ben, do you want to go next?
Yeah, sure. Is the microphone on already? Good. So I have a confession to make. I'm the bad guy in the group. I will try to convince you that observations have only limited use, at least for regulation. So yeah, my name is Benjamin Winkel. I'm radio astronomer, so what I have to say mostly applies to radio astronomy. And I'm also a spectrum manager, so I go to these International Telecommunication Union meetings fighting for quiet skies. Unlike in the optical domain, radio astronomy is well regulated, at least. Not well protected in many cases, but well regulated. So we have this Committee on Radio Astronomy Frequencies in Europe, where we fight to keep your skies clean. We do this mostly, as I said, by going to these meetings. Huge groups for the WRC, the World Radio Communication Conference, which will happen in a month. You expect 4,000 people who meet for 4 weeks or something. So this shows the scale of this. This is what drives a big part of our societies. Without these spectrum management, nothing would work, starting from your cell phone over TV and whatnot. And radio astronomy is really just peanuts for these people, yeah? There are billions of dollars involved. Now, when it comes to regulation, you of course have to prove that you don't disturb another service. If you are a cell phone provider, you have to make sure that no other user of the spectrum is affected. And we do the same. We do calculations and try to find out if any new service, any new application would disturb us. Now, why do I say that observations only have limited use? It happens quite often that I get asked by people, well, can't we just try it out? Can I just switch on my base station for cell phone use? And you see if you really detect some RFI in your data. And it's unfortunately not that simple. So the radio astronomy protection criteria are actually very strict. We only have very limited bandwidths assigned. But in these small pieces of the spectrum, we have very high protection criteria. So the level, the power level that must not be exceeded is 10% of our system noise after 2,000 seconds of integration. So 10%, if you scale that up with a factor of 50, you could barely detect the signal. And as you know, a factor of 50 in signal strength is a factor of 50 squared in observing time. So you multiply the 2,000 seconds with 2,500, and you end up with 5 megaseconds that you would need for an observation to prove that there is a signal above our threshold. So that already shows that it's quite limited. Now, this applies for an isotropic antenna. Of course, we have these big dishes. So with the huge forward gain, if something crosses our main beam, we can much more quickly detect something. But lots of this stuff is on the horizon where we cannot point our telescope. So base station, it won't be easy to prove that they violate the thresholds just by observing 4 or 5 minutes. It's not possible. For satellites, the thing is a little bit different because these cross our main beams very often. So one could have the idea, okay, let's check if they violate our radio astronomy bands. The other problem then is I cannot track the satellites with a 100-meter dish. So there are few, really very few telescopes that can do it. And if you can do it, then their main carrier signal will make your receiver saturated, so you have another problem. So that's why we don't do these kind of measurements very often at the moment, and only in the statistical sense. For example, with the Vigos antennas, we had the talk before, they are small dishes, very quick, you can do stuff. Or you just point your telescope somewhere and wait for satellites to cross, but it's much harder to quickly get results. Still, these measurements will be extremely important. We need that to calibrate all the results. Often we don't know what technical parameters the satellites are using, say antenna patterns, they are often proprietary, so we need to somehow find out what these people are doing in space, and for that, of course, you need measurements. But when you go to ITU, you need calculations, and you better start using all these. You should really keep in mind what the ITU is doing when you produce results, because it has to meet their criteria in the end. Otherwise, it's no use.
Thank you very much, Ben. Suhair, do we have you on Zoom? Let's give him a meeting. Suhair, are you there? If not, then it's my turn to ask some really interesting questions, I think. So thank you all very much for the brief introduction. Genoveva, may I start with you? So you were saying that you are actually, doing a spectroscopic survey in some sense, and the spectra that you are taking, they are sort of repeated spectra of objects that are not all transients, right? So isn't it fair to say that if you repeat observations, even if they are spectra, you could somehow average out the satellite contributions? So in other words, does HOMOS really need extra instrumentation like an imager?
Right. So, okay, we are not like the LSST. The only reason I compared us to the LSST was just to give a counterpoint of, oh, look, we're also a spectroscopic, we're also a survey instrument, but we have much longer exposure times. But we do not only target transients. And in fact, most of our observations are going to be single visit observations, right? People just go somewhere, observe a bunch of stars, galaxies, AGN, and then move on to the next target or to the next pointing without ever having to go back. Yes, we will have some monitoring fields, but more than 70% of all observations with HOMOS will be single visit observations. And that is why we cannot do this having multiple exposures and then seeing which one is contaminated. We can't do that.
Do you have a rough idea of what adding an additional instrument entails for you in terms of cost, in terms of additional time and complexity?
The complexity is the thing that's really doing it, because we in terms of cost, it's going to be like a little amateur astronomer telescope. It's like 10 inches or 13. And the camera is not really that expensive. So in terms of cost for that hardware, it's not a problem, really, not. But it will get expensive if it has to have its own telescope control system that somehow has to talk to ESO, because we are at ESO's telescopes, right? So it has to be organized with ESO. They also do not have any extra resources for this, so we're a bit pressed to figure this out by ourselves. We tried some mechanical designs to try and just piggyback on Vista, the telescope Vista, so that we do not need a new TCS, meaning every time HOMOS points somewhere, the piggybacking system also points there. But that's not working because it's too heavy, and there are all kinds of problems like that we did not account for. But so in terms of cost, I can tell you it's what is it, 20,000 euros, less than that. But in terms of how we're going to actually do it, and who's going to do it, because we need more mechanical design that has to be carried out.
Okay, thank you very much. Next question is actually for Dave. So you said, HST is somehow impacted by satellites, and it has been so, and it probably will be way, way more if I read your trend correctly. Could you tell us a little bit of how satellite trails have impacted science so far?
Yeah. Basically, the good news is they haven't, at least up to now. And I think there's good reason to think that even with an increase in satellite trails, the type of science that's done with HST is still going to be very doable. So just to, kind of explain why I think it's going to be fine, is that, I mean, right now, 1 out of 10 exposures has a satellite trail. A single satellite trail affects about 0.5% of the pixels in the wide field channel CCD. Cosmic rays, on the other hand, affect 5 to 6 times that many pixels. So satellite trails are not the biggest annoyance we have. We have these cosmic rays, which other people are dealing with as well. And we also have a standard way of dealing with them, which is taking multiple images and stacking them and removing the outlying pixels. That works for cosmic rays and bad columns in the CCDs, and it should work for satellite trails as well. I think even if we get an order of magnitude more satellite trails, so maybe every exposure has a satellite trail in it, or a few satellite trails in it because of their randomness, as long as you're doing science where you're kind of just pointing at a target and collecting photons and taking several exposures, I think things will be okay. I mean, people can argue with me. I do think we need to do simulations to see what the impact would be, because I think it can be a little complex, depending on the orbits, the reflectivity of everything that's up there. But yeah, I think HST science will continue seeing satellite trails as more of an annoyance than a threat. I'll say that I'm only talking about HST. I know there are other imagers out there where they may be a bigger problem, and probably time series is something that HST doesn't do a lot of, and that's definitely something to be concerned about. So my statements are only about HST. I don't want to upset anybody too much saying satellite trails aren't a big deal, but I think science will go on.
Thanks very much, Dave. I think there's one follow-up question that burns on everybody's minds now, and I'm going to ask it right away. So how about Blue Orca 3? Isn't there a limiting magnitude where at some point it starts to become a problem?
So I don't know much about that. I looked it up real quick, and I think it's below the orbit of HST. So that's the simple answer. We're not going to point anywhere near it. Yeah, I mean, I think that's why I don't think that specific satellite will be an issue. I think we should totally do simulations with projections of what the satellites are going to be, their orbits, their brightnesses, and so on. Something as bright as Blue Web 3 is I think quite rare in general for HST to see. And again, if we're taking multiple images, I think, yeah, maybe it'll wipe out an image, but an individual exposure, but hopefully we get multiple exposures, and we can recover the science that we need to do.
So Sam, when you talk about, I think you briefly mentioned already how you, do gamma ray astronomy, and what the impact is really, what the impact the satellites have really on gamma ray astronomy. And my question to you is, so if you have limits, and if you see that there is something, will the limits that we impose on optical astrometry or astronomy work as well for gamma ray astronomy?
So that's a bit of a complex question, because it depends on your reconstruction method. So I said that when we observe these air showers, we reconstruct the properties of the original gamma ray. And historically, the way that this is done is that you take the images from your cameras on the ground, and then you measure the width and length of those images, and from that you can infer the particle properties, and also, given the orientations of the ellipses that you observe in the cameras, you can tell where the gamma ray came from. This method is basically underlying most current generation telescopes. So this is called Hillis analysis, after Michael Hillis. And normally what you do is you have Monte Carlo simulations where you train classifiers and reconstructors based on BDTs on the simulations, and then use that, using this Hillis analysis, to tell the properties of the gamma ray. And if you do things that way, then the limits suitable for optical astronomy, say the sort of MV between 6 and 7 that was being discussed earlier today, will probably be okay. It's probably not enough for a satellite trail to disturb the intensity distribution in the camera images enough that this parametric analysis will be affected. So to that level, the limits for optical astronomy will be okay. What we don't know and what we're not certain about is if you start to use more advanced reconstruction methods based on either template analysis or deep learning. So there are new methods being developed and have been used on HESS where instead of just boiling these showers down to 2 parameters, you take the complete image that you observe and then you compare that to a template from a Monte Carlo simulation. And this is an unknown. We don't currently have the statistics on satellite trails to be able to tell how these more advanced, more sensitive reconstruction methods will be affected.
Excellent, thanks, Sam. And my last question is actually a twofold question for Ben. So Ben, you said that observations only make partial sense if you really want to go for monitoring whether satellites are like impinging on the sort of quiet zones and protected zones around radio astronomy stations. But what if I ask, are the satellites really as quiet as that? Aren't they so bright that you really can measure them right away, even though you shouldn't be able to? That's my first part of the question.
Well, so you have to make a distinction between the actual transmissions of the satellites, which always happen in the allocated bands. We are not supposed to observe there, and we can't. So whenever a new frequency is assigned to someone, we usually lose that frequency. So what we do in spectrum management is we do calculations for our frequencies and look if there's some leakage of the satellite transmitted signal into our band. So there's no case where you can transmit just in your frequency range. You always have some spectral side lobes. And this is the basis for the calculations. And this is the leakage is, of course, much suppressed compared to the transmitted signal. But then if you want to observe the satellites, you see these bright carriers right away within milliseconds usually. But that's also then a dynamic range problem. You have a factor of 1 million difference between what you are supposed to protect and the actual transmitted signals, making it much harder, yeah.
Thanks. And the second part of my question is, so if you say that calculations are the answer, there must be 1 million models out there, right? So how do you pick the right calculation model for this? Aren't people fighting over that all the time?
Yeah, they do. At the ITU, we sometimes spend days, if not weeks, about these discussions. So, of course, all the stakeholders, they are somehow inclined to tweak the calculations into their own direction, obviously, or at least to consider all the effects that they think that play a role for them. So do we. And these different estimates can be quite distinct, as you can imagine. So the most important point is that you always try to use the methods and procedures that the International Telecommunication Union has developed, even if they are worse than some fancy science model. For example, for atmospheric attenuation, there is an ITU model, and then there are the much better ones that are used at our submillimeter sites, for example. We have to stick to the ITU models, even if we think it's worse. But otherwise, it's much too easy for other stakeholders to question our results. So that's one point. And it's also very important when you do measurements to produce properly calibrated measurements so that you can really compare them to the regulatory levels. A detection of something doesn't do the job. You need to do better in that case.
I would like to open the floor to questions from the audience now. If you have a question, please raise your hand. Please also state who you are and where you come from. Any questions to our panelists?
This one.
Thanks. Hi, it's Richard Green from the policy part of the CPS. But I have a question for Genoveva and the plans for Foremost. Is there some level of accuracy of predictive ephemerides that would allow you to abandon your simultaneous imaging if you knew the satellite position and arrival timing to some level of accuracy?
Yes, so if we could know the position to better than 1 arc second, so it would have to be a sub-arc second position thing. Then, and of course, we also need to know the exact time. Then yes, but from what I understood, that's currently unavailable, and I don't know. I don't really trust that this will ever be available, and because Foremost is really in the last throes before commissioning, we really have to have a plan that is realistic in the sense that we can make this work and we don't have to rely on somebody else.
Excellent. Next question, please. I think there was one over here.
Sorry in advance if I don't formulate it properly because of the technical terms, but I'm kind of wondering...
Sorry, could you please state your name?
To stand?
No, just state your name and affiliation.
Tomorrow. Policy. So I'm wondering, is there a way for us to know when we know which frequencies are kind of more congested, what could be the trends, and which other frequencies satellite companies and mainly like communication and internet companies, let's say OneWeb, Starlink, would kind of use and what would be trending so we could know like in advance to kind of be prepared what might get congested, what might get freed up? Is there a way to assess this in advance? And is there a way to know like which frequencies they would move to, what would be like kind of trending, and in general, which ones would get most congested and problematic when it comes to interference? And I'm sorry in advance if I didn't read the graphicons properly, so I don't know. That's, kind of.
Okay, yeah, it's a really good question, actually, and was all phrased well, no worries. Yeah, it's a complex one, though. First of all, no one can just start using frequencies. You have to have an entry in the frequency allocation table that is done by the ITU. And this can take up to 10 years. If you want a new frequency, you often need 1 or 2 of these World Radio Communication conferences before you can actually have that allocation. However, there are already lots of existing allocations, so any satellite operator can use the existing frequencies. So you have to understand that it's not like someone goes to ITU and asks for an entry in the table, but these tables are for these frequency allocations are for everyone. And then if you have an application, you just submit a so-called filing to the ITU, and if the ITU thinks it's okay, you can start using the frequency. So that way we know at least where satellite operators are supposed to be, but that doesn't mean that we know from all future plans if they perhaps are after getting a new allocation somewhere or into what frequency they really want to go. So it's still a complex issue.
Thanks. Yes, please.
I have a question to Benjamin.
Could you please state your name?
Michael Lindqvist from Unsula in Sweden.
I'm sorry, could you please state your name for the
Michael
audience?
Lindqvist from Unsula in Sweden. So I have a question to Benjamin here. You mentioned the World Radio Conference and it's the meeting that will take about 1 month and with 4,000 people. And as far as I know, there is now a proposal from Europe when it comes to for a new agenda item for the World Radio Conference 2027. And then CRAF has been very much involved in that. So could you please tell us a little bit about that?
Yes, of course. The Committee on Radio Astronomy Frequencies is a European organization which tries to lobby for our access to the skies in Europe. And the WRC, the World Radio Communication Conferences, you don't just go there and do stuff. Everything has to be studied first. So before you can do that, you need to go to a previous WRC, make it so that you have an agenda item for one of the next WRCs so that you are officially allowed to start study stuff. And now we successfully talk to European administrations so that the European spectrum agencies will propose a new agenda item for the WRC in 2027, where we would study the effect of mega constellations or very large satellite constellations on radio astronomy and potential ways to protect it better. So doesn't mean that the World Radio Communication Conference next month will actually adopt this, but the chances are at least there because we have this European proposal, and there is actually another one from the African countries. South Africa was heavily involved in this because they have the square kilometer array with the radio quiet zone, so they want to look into how can you protect your radio quiet zones from satellites, because these radio quiet zones are a national thing. It's a sovereignty problem, so space is not part of your sovereign country. So there is currently no way in this legal domain to protect your radio quiet zone from space. And they want to look into this. So lots of interesting stuff happening.
Thanks. We have time for one more question. There's also one on Slack. While we are waiting for this, maybe we'll take that. We'll just Slack question. So there are two on Slack. One is for Genoveva, I think. And Angel, are you online on Zoom? Do you want to unmute and ask a question? If not, I'm just, yeah, go ahead.
Hello. Mm-hmm. Oh, here I am. Yes, interesting talks. I basically commented a couple of times regarding the need of information from the satellite operators on the physical properties of the materials that composed the body of the satellites. This because the reflecting properties, like we observe in our color information, is modulating the solar spectrum. So it makes it a little bit harder for people like Genoveva, with spectroscopy observations to really disentangle this solar spectrum when it's convoluted, with the physical properties of the reflecting body. That was basically one comment I did. And it was an invitation to the satellite operators to share information and make our life easier, actually, to interpret data, but also to deal with it.
If not, maybe we can have another question here from the audience, please.
Thanks very much. I'm Fred Watson from the Australian government, formerly the Australian Astronomical Observatory. So I'm an optical astronomer, and I'm always...
So I actually, to answer that, it says, or at least there's a... Sorry? Okay, so there's at least a suggestion that maybe Foremost could close shutters to avoid the satellite contamination, then open them again. But no, we have a huge, enormous shutter that takes 1.5 seconds to close. That's not feasible for us. But yeah, it would have been nice if we could just like CMOS, just shutter the pixels that have a satellite on them and then unshutter, but we cannot do that.
I'll carry on. Obviously, interesting internet delay things going on there. My questions about the ITU, I'm afraid, as an optical astronomer, I've never really had that much to do with it. But my radio astronomy colleagues tell me that one of the big problems that they experience is not the fact that frequencies leak into the radio astronomy bands, but that the spacecraft themselves are very, very noisy across a broad band of the radio spectrum, particularly CubeSats. I wondered, does the ITU have a regulation about that background level of radio leakage?
So it's probably another question to me, I fear. So, the ITU doesn't do that. ITU mostly cares about intended emissions, so everything that is somehow tied to your antenna, your signals, your carriers. So everything that is beyond that, like stuff that leaks out of your electronics or electrics, the ITU is not responsible for this. You have some standardization organizations like the CISPA, or also NASA and ESA do their own standards for spacecraft, but it's only in-house, if you will, and has no external application. But I would also not fully support the statement that you made, that the more troublesome aspect is these, say, leakage radiation. The transmitted signals are orders of magnitude brighter, and also the spectral side lobes are much, much worse. So the radiation, the X-ray radiation, is just something that comes on top.
Thank
and
you.
It's at very low frequency. So if you have a satellite that operates at, I don't know, 10 gigahertz, 20 gigahertz, you can have this leakage radiation at 100 megahertz, which is completely unrelated to the carrier signal then, which is also an aspect that is new.
Thanks again, and I think we are running out of time very rapidly. Please grab our panel speakers during lunchtime or online on Slack. I would like to give a big hand to everybody here on stage. Thank you very much for joining us and for sharing your interesting points of view.